All right, we are continuing with that final problem from our piecewise function notes. We are going to be writing the equations when we don't have the graph, we just have data. So in this case, we've got an amusement park that's tracking its ticket sale revenue in dollars per hour over the course of opening day. So we're measuring T in hours since they opened, and this is going to kind of walk us through each portion of our data here. So starting with our opening from hours 0 to 2. Is this linear, quadratic, or exponential? Well, I can see that these revenue values are increasing by the same amount every time. So our first differences are the same, so that tells us it's linear. And the equation for that is going to be slope-intercept. I can see here that my slope is 500x. And I'm starting at 0, 0, so my y-intercept is 0. There, I'm done with my first equation. For the second portion, from hours 2 to 6, is this linear, quadratic, or exponential? I can see I'm increasing to a peak and then I switch to decreasing. So this is going to be quadratic. And to write the equation for a quadratic, I can do that in vertex form if I know the vertex and the a value. Well, if it tells us that the vertex is at 4, 2,000, that's my h, that's my k, that means I just need to know my a value. Now, similarly, when we're working with linears and we are finding b by plugging in one of our other coordinates, we're going to do that here for a. So I'm going to pick another point on my interval between 2 and 6, like let's just say 2 and 1,000. I'm going to use that x and y and plug in my h and k to solve for a. So 1,000 is equal to a times 2 minus 4 squared plus 2,000. And using my order of operations, this one is actually going to end up being a linear equation to solve. I don't have to square root anything. Subtracting 2,000, and I get, after I divide, that a is negative 250. So my equation is negative 250 times x minus 4 squared plus 2,000. And then lastly, our evening slowdown. So I'm looking from hours 6 to 12. Is this exponential, linear, or quadratic? Well, I can see that I am decreasing by the same amount over each of those hours. So this is linear again. And to find that equation, I need to know the slope. Now, negative 200, but this is happening now over a course of every 2 hours. So my slope is negative 100. But I need to find my b value. So this is where I'm going to plug in one of my x and y's again, like let's just say 6 and 1,000. So 1,000 is equal to negative 100 times 6 plus b. And I get that my b value is 1,600. So with all that in mind, we can now write this piecewise function on our 3 parts. So R of t, our revenue, is 500x at the start, and that was for x values between 0 and 2. For our middle portion, we had 250 times x minus 4 squared plus 2,000, and that was for x values from 2 to 16, and I need to not underline that because we don't want to account for it twice, and not even 16, sorry, 6. Then our final one at the evening was negative 100x plus 1,600, and that was for x values from 6 to 12. So what do each of those represent in terms of customer behavior at the park? Well, at the opening, that means that we have steady increase, because we are increasing at a constant rate. Then by midday, we increase to a peak and then decrease. And in the evening, we are seeing steady decrease through the end of the day. And so why is a quadratic a good fit for that midday boom? Well, because we have a peak, aka the vertex here. And why would an exponential decay model be more realistic? Well, it actually wouldn't, because if you think about exponentials, they have that horizontal asymptote. So if I had an exponential, it would never reach 0. But in reality, at some point, our revenue is going to reach 0 when everybody leaves the park. So it's actually not. So to predict the revenue when time is 9, well, that falls into our third equation. So when time is 9, negative 100 times 9 plus 1,600 gives me a projected revenue of $700.